Hi everyone, this is Ms. Rosita. We're looking at section 1.7 today, inverse trig functions. So we've just finished the two sections in the book about graphing our usual 6 trig functions, and now we're going to be looking at the inverse of the trig functions and their graphs. Before we get into that though, I wanted to just make sure everybody was remembering what an inverse function is. And we look at it both algebraically and graphically. So on the left side of the screen here, we have a reminder of how to find inverses algebraically. So if we have some function f of x is 2x plus 1, f of x we can replace with y, another name for it. If I want to find the inverse of this function, what I do is I switch the x and y, and then I isolate the new y value. So move the 1 over, divide by 2, I get what y is. That new y is what we call f inverse of x, so the inverse function. Graphically, if I want to find the inverse of something, then I basically start with my original function and reflect it across the line y equals x. So here in the picture I have my original function is y equals x cubed. That's the black function shown. Then I reflect it across the blue line y equals x, and I end up with the green curve, which would be the cube root of x, or the inverse of x cubed. Okay, so it should be symmetrical across that line. All right, whenever we're talking about inverses, it's always good to go back and remember the vertical line test and the horizontal line test. So the vertical line test is the one that tells us whether or not our equation represents a function. Now I put a relation passes the vertical line test, we call it a function. Remember, a relation is just any equation that relates the variables x and y. And so if that equation does pass a vertical line test, it is a function. Remember, a vertical line test, in order to pass it, you have to be able to draw a vertical line through your graph at any point and have it cross in no more than one place for it to pass the vertical line test and be a function. Okay, so let's say we do have a function and we're looking at it and we do a horizontal line test. And again, we're asking ourselves, if I draw a horizontal line anywhere through the function, will it cross it more than once? And if it does, it fails the horizontal line test. What the horizontal line test tells us is whether or not its inverse is a function. So I have the original function. I'm too lazy, let's say, to reflect it across the line y equals x and look at it. So instead what I do is a horizontal line test on the original function. Because after all, a horizontal line would be like a vertical line if I reflected a horizontal line across the line y equals x. Okay, so I have our sine wave drawn here, just 2 periods worth. And my question is, does it pass a vertical line test? The answer is yes, it is. It is a function. It does pass the vertical line test. Next question, would it pass a horizontal line test? Answer, no. Okay, even the x-axis you could use as a horizontal line. You could see the sine wave would cross that x-axis infinitely many times. So the idea is if our function does not pass a horizontal line test, it doesn't have an inverse, or we'd say the inverse isn't a function. That would be bad, because we're talking about inverse functions today. So we want our sine wave to have an inverse. So what we're going to do is we're going to restrict the domain of our sine wave to be just that portion centered around the origin from minus pi over 2 to positive pi over 2. That's from the minimum to the maximum of our sine wave going through the origin. So that portion of it from min to max would pass a horizontal line test and will have an inverse. The inverse will be a function. So that's our restriction of the domain. So there's a couple things to know. The capital letter, when you see down here toward the bottom, y equals capital sine x, the capital letter means that we've restricted the domain of our sine function. So here, running across the bottom of my screen, on the left I have just the usual sine wave, where the domain's all real numbers and our range goes from -1 to 1. I then have in the middle the graph of capital sine x, where I've only graphed from minus pi over 2 to pi over 2. Okay, so I restrict the domain just from the min to the max. The range is not affected. It's -1 to 1. Okay, that would be capital sine x. And then finally, my third picture would be the inverse function. So if I take my middle graph and flip it over the line y equals x, I get the last graph. Now, I know I haven't scaled things on here, apologies, but you can see your domain and range from the middle graph are reversed for the last picture. Okay, so on the x-axis in the middle graph, you have minus pi over 2 to positive pi over 2. On the y, you have minus 1 to positive 1. On the last picture, okay, it's the domain that goes from minus 1 to 1 on the x-axis. And the range is going to be the y-axis values minus pi over 2 to positive pi over 2. Notice the concavity also is switching. So for your sine wave in the first quadrant, it was concave down. Now in the first quadrant, we have concave up. And same idea in quadrant 3. Okay, well that's just your sine function. We would do the same for all the trig functions. You can look at cosine, okay, all real numbers minus 1 to 1. Restrict the cosine curve, again taking it from the max to the min so that it will pass a horizontal line test. That would go from 0 to pi, half the period. Minus 1 to 1 for the range. And then the inverse of that, your x and y's trade places, so that means domain and range trade places. Minus 1 to 1 on the range is now actually minus 1 to 1 on the domain. And the domain was 0 to pi, now that's the range. Okay, what we get is our new picture on the far right. I should also mention, in terms of notation, the inverse function has that superscript of a minus 1 in front of the angle. You could also call that arc cosine of x, same thing for our purposes. So y equals arc cosine of x and y equals inverse cosine of x would mean the same thing for what we're doing. Okay, let's see, tangent. Well, the tangent has the vertical asymptotes at pi over 2 and negative pi over 2 and negative 3 pi over 2 and so on. So the domain usually is all real numbers except where those vertical asymptotes are, which are pi over 2 plus the period multiples. And range usually up forever, down forever, all real numbers. So if I want to take a piece of this so that it will pass a horizontal line test, I'm just going to take one period worth. And why not pick the one that goes through the origin? Seems like the obvious one to choose. So here, I'm restricting the domain to be between minus pi over 2 and pi over 2. And range still is going to be all real numbers. Notice that the domain here, this is interval notation for the domain. I'm using parentheses, not square brackets, because the endpoints would actually be the vertical asymptotes, and our tangent's not defined there. So make sure we use a parenthesis, not a square bracket, so that we're not including the endpoint. And the capital T again for the restricted domain tangent. So now when we have tan inverse, lowercase t, minus 1 exponent, the x and y's have traded. So again, all reals now for the domain, and our range is going minus pi over 2 to pi over 2. So the vertical asymptotes that the tangent usually has at minus pi over 2 and positive pi over 2 are now going to be horizontal asymptotes on the inverse function. So I have a horizontal asymptote at pi over 2 and another one at negative pi over 2. Okay. Hopefully all that's making sense to you. Now, if that sounds like a lot, the next slide is probably a good thing. So, of course, we've got 6 trig functions. We went through only 3 of them. So the other 3, you might see them appear here or there on a homework question, but I'm not planning to test you on the other 3 trig functions inverses. Okay, so just make sure you're practicing your sine, cosine, and tangent. If you come across one of the others in a homework assignment, great, give it a try. See if you can figure it out, but they wouldn't be on your test. Okay, so looking at our inverse functions now, inverse trig functions, we've already talked about it graphically, so now we're going to go back and think about it algebraically. So our first example here, it says evaluate arctan of minus 1, or I could have put tan inverse of minus 1 with the negative 1 exponent. They mean the same thing. So what I want you to think, off on the right here, I put it in quotes. I want the angle whose tangent is minus 1. So whenever I see an arctan or inverse tan, I'm going to think, I want the angle whose tangent is minus 1. I'm looking for an angle. Okay, you might be thinking, we've already done these inverse trig functions when you had a calculator. You know, the first part of the chapter when we had a triangle, we were solving for the angle in the triangle. We knew the, let's say, the adjacent and the hypotenuse, whatever it is, and we would set up, say, cosine of the angle is the adjacent over the hypotenuse, whatever that was. And if you're looking for the angle, you would have done inverse cosine, right? You'd hit the little blue second key on the calculator and then the sine key, or whatever it is, cosine key. So that inverse function is the same idea, and when you use your calculator and you hit that second key and then the cosine or second and tangent, whatever it is, that means you're looking for the angle. So what I want you to remember is that when you see an arctan or inverse tan or arc cosine or whatever, the answer is supposed to be an angle. I want the angle whose tangent is -1. Okay, so looking at a unit circle, I know where the tangent is -1, right? It happens in two quadrants, quadrant 2 and quadrant 4. In quadrant 2, it would be at 3 pi over 4, and in quadrant 4, you'd be thinking 7 pi over 4. The only problem is I have to give my answer in the restricted domain. So if I go backwards in my notes here, and looking at the tangent picture, okay, we said the domain for capital T tangent was going to be restricted between negative pi over 2 and positive pi over 2. That means our angle that we're coming up with as our answer needs to be somewhere between minus pi over 2 and positive pi over 2. So I can't actually come up with quadrant 2 as part of my solution because negative pi over 2 is straight down, and then I move around through quadrant 4 to 0 and then into quadrant 1 to get to the top at pi over 2. So I'm on the right side of my unit circle. I won't have any answers on the left side for arctan. Furthermore, the one that's in quadrant 4, we might have been thinking of that as 7 pi over 4. But 7 pi over 4 is much bigger than pi over 2. So I can't use 7 pi over 4 as an answer either, but I want to be thinking coterminal with 7 pi over 4, just in the negative. In quadrant 4, I read it as a negative angle. It's negative pi over 4. Coterminal with 7 pi over 4. Okay, let's try another one. Cosine inverse of 0. I want the angle whose cosine is 0. So I'm thinking at the top of the unit circle and the bottom of the unit circle has a cosine of 0. However, the cosine's domain restriction for capital C cosine was from 0 to pi. So that means I'm on the upper half of the circle and I only can give the answer pi over 2, not 3 pi over 2. The last one there, I want the angle whose sine is root 2 over 2. I would have pi over 4, but also 3 pi over 4. However, again, the interval for sine, okay, we said was from minus pi over 2 to positive pi over 2. So I'm on the right half of my unit circle. So I'm looking at just the angle pi over 4. All right, so next one. Write theta as a function of x. This looks very familiar from what we had done in the first part of the chapter. So here I have an adjacent side of 4 and a hypotenuse of x, my angle theta. So adjacent and hypotenuse, I would pick cosine of theta most likely to be 4 over x. And if I want to write theta as a function of x, that means I need to get the theta by itself. So I'm going to take cosine inverse of both sides. So cosine inverse of cosine cancels, giving the angle. And on the right side, cosine inverse of 4 over x is what I have. I don't know what x is, so that's as far as I can take it. That's my answer. Now, same triangle on the last example here, but I could have, instead of doing adjacent over hypotenuse, I suppose I could have done hypotenuse over adjacent and said secant of theta is x over 4. So theta would be inverse secant of x over 4. And we've got it. Okay, so composite functions is the last topic, and I'm actually going to save these 2 slides for the next video because it's going to be the next day in our class. Your practice problems, I just covered problem number 1 today, so you would just need to make sure you fill in the first problem. The other 2 problems will be next time. Okay, thank you everybody for listening.